Good morning, everyone. Come on in. While we're waiting for people to come in, feel free to ask me any questions. Good morning, Georgie. Hey, Kayleen. Hey, Will.
Good morning.
Good morning, Randall and Richard. Anybody have any questions? Hopefully you all saw that I did post the video as bad as it was. Of course, I even named it as such, but what I would ideally think it would be best for you to watch is the N05B video for the 11.1. I got all the bugs worked out for that second recording, and I actually posted another set of notes for that, so you can look at the same name as the tape was recorded as, or the video was recorded as the document in my Google Docs. That's, of course, the way I always do it. I did recently change, by the way. I used to write PHY underscore 241 underscore section number, which in your case would be D01B. Then I write underscore some kind of indicator of what chapters we covered, like I'd say capital C, lowercase h, 36. And if that was the last day of that one, I would end it with capital FIN. And if I started a new chapter, I'd label it capital S after the N and put like 11 or whatever. And then I'd have another underscore, and then I'd put the date 11/01/21. So that's the way I used to name it. Well, obviously that's a buttload of letters, and it made it where I couldn't go back and easily read which document was which. So I changed it to just a plain P for physics, because I teach two types of classes. I teach physics and astronomy, and our astronomy comes under NAS. So when I do astronomies, I'll label them with an N. But anyways, it's P and then 241 and then D01B all in one slot. There's no underscores between any of that. And then there'll be an underscore lowercase c 36 for the chapter 36 underscore 11/01/21. So just keep that in mind. That's the new naming protocol for not only for the notes, but also for the videos I make. So you'll see when I put up my videos on YouTube, in the description, it'll start off with me telling you that y'all can email me at billy@physicssolutions.com to get any documents that they want. And then the next line will be the actual name that I named the video. Even though YouTube already puts it off in the side, I put it there as well, so y'all can immediately see it. So I would recommend you check out the lecture from Monday night. That's the N05B one. I went through the whole thing and went through what we're covering partly today. I almost feel like I'd rather not waste more time on the twin paradox and the Ladder-Nabarn paradox, but I figure it's more appropriate for me to make sure I cover it, even if I have to go an extra day with you guys. So anyone have any questions on any of that stuff or any past material? I graded another set of labs. I also noticed that some students seem to be forgetting to turn their labs in by the beginning of lab class, and that costs you like 50 attendance points each time you do that. So remember, I only allowed you 2 total. That could be 2 late lab turn-ins, or 2 late or 2 absences from lab, or it can be 1 of each. From there on out, you lose 5 points a pop to your attendance score. So I've got some people that are in the 60s on attendance score now. I don't want that. Should never happen. I want you guys to do that. Also, I have multiple labs throughout the week. I have the one today at 1:30. I have another one tomorrow at 8:30 a.m. I have another one Friday at, I believe, 1 p.m. So those are all 241 labs. I also have 242, but there's only one of those. So, but if y'all have to miss a day, let me know and I can send you an invitation to another day so you don't have to lose those points. All right, so I guess I'll go ahead and get started since it does not appear we have any questions. So I'm going to start.
I have one question, Professor.
Yes, go for it, Mary.
For the lab, because I'm in your lab and your lecture for today.
Yes.
For linear graphing 2, I know it's typically due on the lab day, but you've been changing them and you made it due for tomorrow at 8:30. I just wanted to double check on that, so I'm not going to end up like.
Yeah, it was supposed to be. What I meant to do was I was going to do till 8:30 the next morning, of that meeting time. So are you talking about my lab for today or my lab for tomorrow? Mary?
From last week, and it was typically, yeah, you make it due, so it's due before the next lab, but you've been making them for Thursday now. And I just wanted to double check on that too, because if we do hand in one late, is it one from a week since that Thursday date or from the Wednesday date?
No, I'm gonna, in fact, I made a mistake and got it mixed up. I'm gonna make it, it'll be due today at 1:30. I mean, at 1 o'clock by lab time. If you come in and you realize, oh crap, my lab's late, I'm gonna give you a few minutes to go ahead and turn that in. But what I meant it to be was for class time today. I wanted to give you all the whole 2 weeks since I ended up canceling lab.
Well, I think we did have lab for last week. We
Yeah,
did. We got to put ourselves in different groups. We got to like choose our own partners this time.
Yeah, that's right. Yeah. Sorry, my 242 was a class that had to cancel. So yeah, it'll be due at the normal lab time. But since I screwed up a little bit, I'll probably make it 8 a.m. tomorrow morning just to make sure y'all can have extra time.
Okay, thank you. I appreciate that, because I went online and I checked and I was like, wait a minute. So I wanted to ask you first, but I just want to make sure that if I do hand it in for the due date that said tomorrow 8:30, if it would still be late or not.
Yeah, that'll be on time. Don't worry about it. Since I said it that way, I'll just leave it at that time. And everybody, make sure you get yours in. If y'all have any last minute corrections, go ahead and do it and submit it by then. Remember, I only look at the very last one you uploaded. So that's what I'll be grading. So far, everybody's doing really, really well in the lab reports themselves. Like I said, that first one was probably a low grade because I had to pop everything, and I still try to pop everything. But I think by the first and second lab, you've seen the things you lose points for, and hopefully you won't be missing any more of those. So I suspect the rest of your labs will be 95s and 100s. So.
Sir, I'm not sure if I'm the only one, but I don't have a grade for the second lab at all. I only have a grade for the first lab.
I will check that. I thought I did the second lab already. No, you're probably everybody's in the same boat. If I could have very well missed a particular class, but I did lab 2 and started into lab 3 on everybody's, but I might have missed the lab that you're in. So are you in today's lab, Cadmium?
No, I'm in the Friday lab, sir.
Okay, good. Okay. All right. I will have that done by Friday if I hadn't already done it, but I did think I'd already done it. So it might just be a matter of I didn't push the submit button thing. Okay. Thanks for letting me know. I do get a behind in the first several weeks just because that first lab takes so much time and the second lab almost takes as much time. But from here on out, it should go pretty quickly, hopefully. Anybody else?
Hey, sir.
Yes,
sorry
sir,
I'm late.
yeah.
I just popped in. I was finishing up a test with Miss McIntyre.
No problem.
There may be some other people coming in after me as well.
Okay, I am getting some more people coming in. Just to let you know, Gavin, I told them that if you have lab today, I'm marking it. I've already marked it by accident to 8:30 tomorrow morning, so I'm just going to leave that. I don't know if you have that lab or not, but anyways, I told them that. I also told them that lab 2 has been graded, and I'm supposed to be starting on lab 3, or I have started lab 3, but there might be a class where I didn't do that on. So just letting you know that. Anything else? Anybody remember that I just announced before he got here?
You said something about lab tomorrow morning or something. What
Oh yeah,
that?
I was just telling everybody, if you ever have to miss a lab, I've got 2 other PHY 241 labs. I have today at 1 o'clock. I have 8:30 a.m. tomorrow, and then I have 1 p.m. Friday. All of those are open and available. So if you have to miss, a Monday lab, or excuse me, a Wednesday lab, you can attend the Thursday morning or the Friday afternoon. If you have to miss a Friday, you can attend the Thursday morning or a Monday afternoon. I'm keeping them aligned so everybody's on the same lab each week.
Okay. I don't think I need to miss anything, but on the off chance that I do, how would you join that meeting? Is it the same meeting ID?
Yeah, you just let me know that. Oh, no, it's not the same meeting ID. You let me know which one you want to attend, and then I send you an invitation by mail.
Oh,
by email.
Gotcha. Okay, thank you.
I have successfully pulled that off twice now, so it's not a magical thing that doesn't actually happen. It actually happens. I'm able to remember it long enough to do that. I'm feeling very teacher-like lately. All right.
Well, that's good, I guess.
Yeah, I'm doing my job. Woo! I should get a bonus. All right. Well, let me get you started on the twin paradox again. Oh, that's the other thing I didn't mention to you, Gavin, that I said before you got here. I told everybody, remember the poop show that was the last lecture, all the mistakes I made and all that good stuff. Well, I did another lecture that same day, which is 1101. 110121 is what the stamp on the document as well as the stamp on the video is, but it's N05B, N05B, N as in night, 05B. That was done at 5:45 on Monday, and it was basically clean. So I put that video up as well as your own, but I would suggest you watch the other one and look at the notes for the other one. I'm trying to make sure they get up the same day, if not first thing the very next morning. So this lecture should be up to today. If not, like I said, the same thing, early tomorrow morning. So let's get started. We're going to first talk about two quote unquote paradoxes. And I put the paradox in quotes because we can't have paradoxes in science. If we have a paradox in science, that's science that's screwed up or some deeper understanding that we're missing. Now, in things other than science, it's perfectly reasonable to have paradoxes because that isn't in the realm of testability. Okay, but in sciences, in physical sciences, especially biological sciences, paradoxes aren't acceptable. And the paradox is when two equally valid theories or parts of a science or whatever point to two entirely different outcomes, but those outcomes cannot both happen. That's a paradox. Okay. So when you have that, that means your theory is lacking. And as I told you, that was the motivation for Einstein creating the special theory of relativity when no one thought physics had any problems. So in this case, we again have a apparent paradox, and it's called the twin paradox. And almost everybody misrepresents it. I even found when I was in high school a book put out by Time Life Books, which I've always sort of respected as at least getting experts to do the thing, to do the reporting or the writing or whatever, but this was just BS. So now I've got to go back and think every Time Life thing I ever looked at might be BS. But anyways, beside that, the twin paradox is the idea of two twins being, of course, they're being born. Twins means they're born on the same day, so they're the same age. So I'm going to show you the diagram I have over here and discuss this. So I make it about me and my brother, who's not my twin. In fact, he's not tall and good looking with all the hair like I have. He's short and fat and losing his hair. So I'm going to pick on him about that here. So it's me, Billy, and my brother Brian. We're supposed twins on planet Earth. And what's going to happen is this spacecraft right here is flying by, and it's flying by at 0.96285 times the speed of light. Okay, that's actually root 15 over 4, and that causes a gamma factor equal to 4, which y'all can look at your spreadsheet if you made one, or you can look back in the last video and see my spreadsheet and see that's what gave you 4 for a gamma factor. Okay, so here's the scenario. I am going to transport myself onto the spacecraft. Okay, and now I'm going to fly all the way to Alpha Centauri. Alpha Centauri is it's actually a binary system, but it's the nearest star system other than our sun to us, and it's about 4 light years away. It's actually more like 4.2, but I'm just going to pretend like it's 4 light years for ease. Okay, so in reality, that trip, according to you guys back here on Earth, including my brother, y'all are going to think that trip takes. Now I'm going to do 4 divided by 0.9. So that's 4 light years divided by 0.96285 light years per year. And that gives me 4.15 years. So this trip will take me 4.15 years according to Earth. So I'll subscript it Earth time. Okay. Now, when I get to Alpha Centauri, I'm going to immediately teleport myself again, just like on Star Trek. I'm going to teleport myself from this spacecraft to another spacecraft with the same speed, but going the opposite direction at 0.96825 C. Okay. And then it's going to take another 4.15 years, according to you guys on Earth, for me to get back. Okay. And we both left on our 51st birthday. or I left on our 51st birthday. Sorry about that. Okay, my brother's not 51, by the way. He's like 7 years younger than me, turdball. Anyways, but let's remember, the important thing is he has less hair and he's fat and he's shorter than me. That's my story. Okay, so when I get back, I am now, believe it or not, because this gamma factor, I'm supposed to be, according to your clocks, 4.15 plus 4.15, which would be basically 8.3 years. But because my time dilation factor was 4, that means my age is going to be that divided by 4. So in fact, I'm now 53.07 years old. So Billy returns at 53.08 years old. Now, this is where Time Life books and various other things screw up. They think that's the paradox. Okay, that two twins have a different age. No, that's actual fact. That's just fact. If I did that, if I flew on a spacecraft at 96.285% of the speed of light, flew all the way to Alpha Centauri and then teleported onto another spacecraft and flew all the way back, I would be only 53.08 or 2.08 years older. Whereas my brother, Brian, is now, and I'm going to add, of course, 9.3. So he's now 60.30 years old. Again, people say that's the paradox. It's not a paradox at all. And Life magazine or Time Life books thought it was the paradox. It's not the paradox. The paradox is this. My brother, who's quite vain, by the way, vain and ugly and has no hair and all that good stuff. So my brother wants to claim that he's the younger one, right? So he claims that, in fact, the Earth and Alpha Centauri, in fact, flew this way at 0.96285 the speed of light, and then turned around and flew back this way at 0.96285% the speed of light, or without the percent symbol, speed of light. And that I, in fact, just stood here sitting still on this aircraft after teleporting from Earth. Therefore, he wants to claim that he's 53.08 years old and I'm 60.30 years old. That's the paradox. However, there is a way to tell which one actually moved, and I call it the fuzzy dice solution. So let's imagine if I, in fact, was wearing some fuzzy dice earrings. That's like a thing from the 70s and 80s. People hung fuzzy dice from their rearview mirror, and I think they somewhat do it now out of humor. But of course, my brother wears them all the time. Again, that's my story about my brother. Okay. So evidently, he's a fuzzy dice wearing fat slob with no hair who's shorter than me. So can't wait for him to see this. Anyway, so I'm wearing these fuzzy dice. And what you will be able to tell immediately when I teleport from Earth to this thing is the fuzzy dice are going to swing that way because I'm going from sitting still to taking off that way, right? And then when I teleport from this spacecraft where I'm going this way at over 96% of the speed of light, I'm going to teleport to another spacecraft going this way over 96% of the speed of light. Obviously, my fuzzy dice are going to swing that way again. And then when I get all the way back here, my fuzzy dice, when I teleport from here to here, they're going to swing that way again because they were going 0.96285 C, and now they're going 0. Meanwhile, my brother's fuzzy dice earrings didn't do a thing. So there's no paradox because there's no way that could have happened without us knowing. Now, if the universe happened to be, let's say, circular, okay, like it was on a giant sphere, the surface of a giant sphere is our universe, then you could imagine a scenario where the circumference is about 9.3 light years around. We know for a fact that's not it. But in that case, then I could actually fly all the way to Alpha Centauri, and that would be on the opposite side of the quote unquote universe. And then I could continue going around the same direction and come back here, and I'd be right back where I started from. And in that case, I would never have any fuzzy dice swinging, and we couldn't resolve the twin paradox because we couldn't tell which one actually is right, which one really did do it. So I would say that's an argument for the universe not being closed, because if it was, it would introduce a paradox where someone could actually do this. Okay, so the twin paradox is not a paradox. In fact, all that's really going on with the twin paradox is that one person is trying to claim motion when we can definitively prove that they did not move. Does that make sense to everyone? It's a little difficult to understand, but it's yeah, oh yeah, this is sort of like the plot from Interstellar. In fact, that planet that they ultimately end up on is a is a giant space station that's circular and of course spinning. That's how they can basically pretend there's a gravitational acceleration, is by making you have a centripetal acceleration just to stay on the surface of the planet, or of the spaceship in that case. So it's not that easy to really understand, but that is the crux of the twin paradox and what goes on with it. So anybody have any questions about twin paradox? So all this is actually fact. But remember, the paradox argument is that Brian could claim the other. Okay, now here's the next paradox, and it's called the ladder in the barn paradox. So let me use some fancy ink. Ladder. Whoa. Let me spell ladder with 2 D's as opposed to the non-traditional 1 D. Ladder and barn paradox. So again, this is a paradox in name only because it can't be a paradox. But anyways, I'm going to resolve that for you. So y'all see the picture here. There's a barn. It's 10 foot wide. There's a ladder leaning against it. It's 20 foot long. Okay, that's the crux of the story. So let me turn back so I can do some good Currituck country person discussion. So I like to tell the story this way. So anyways, a young boy goes away to NC State, leaves his father's farm. He's been working with his father's farm for years, and he's really pretty much deciding, I don't want to be a farmer anymore. I'm gonna go off and do something big and go to college and all this good stuff. So he goes away to college, goes to NC State, comes back for his first summer break, and probably like you guys with your first year or first course in college, you feel like you really know a lot of stuff and you think you know a lot more than your parents do. And in many cases you do, and in some cases, of course, you don't, because experience can really teach a lot. But the main point is the boy's getting up on his high horse and acting like, you know, he's brilliant. And he says, well, Dad, I just pulled up and I looked out there at the farm and I see that stupid ladder still sitting outside the barn. Now, why don't you just go ahead and stick that ladder in there? And the father says, well, boy, I don't know what they're teaching at NC State now. You know, I went there too, but no 20-foot ladder is going to fit in a 10-foot barn. And the boy says, well, Dad, I'm sorry. Yes, they are teaching us better now at NC State. They taught us, in fact, I took a physics course and I had relativity there, and I could actually make that ladder fit in that barn. And the father sort of winks at him and says, oh, okay, yeah, sure, that'll be great. Okay. Of course, you know, I'm a bit old now, and, you know, I can't just be jumping and running and doing all sorts of crazy stuff like you can now at all this young age. So you're going to have to demonstrate it for me. Father seeming to know something that the boy doesn't know. So how exactly do you propose to do this, son? So the son tells him, all right, here's what I'm going to do. I'm going to pick up the ladder, okay, and I'm going to start running until that ladder reaches 0.86605%, or excuse me, times the speed of light, because I happen to know that's a gamma factor of 2. So that 20-foot ladder will shrink down to 10 foot long, and it'll fit in the barn. So at the instant the front end of my ladder reaches the back edge of your barn, the back edge of my ladder is going to reach the back edge of the front edge of your barn, and you're going to close the door, and the ladder will have fit in the barn. And father says, okay, yeah, that sounds like a good plan. You might be able to pull this off. Let's see. And the boy says, okay, so here's what happens. Let me turn on the document cam again. So the father really does know something. The father says, okay, go ahead, let's start, boy. And the boy picks up the ladder and he begins to run. Now, the boy hasn't really thought this out as well as he should, which is why the father's laughing so much. The boy is in fact running at 0.86605 C, which is, by the way, beta equals √3/2, which implies gamma equals 2.00. Okay, and that's not that good a focus, so let me fix that. Okay, so the boy is actually running, and what he realizes is, oh crap, the ladder is still 20 feet long. And the father's like thinking to himself, duh, you dumbass, you're running with the ladder. The ladder's not moving with respect to you, so it's going to be 20 foot long. But much to his chagrin, he sees this barn from the side now looking like this. In fact, now the ladder, or excuse me, now the barn is exactly 5 foot wide. That's a problem because clearly he needs to fit a 20-foot ladder now, not in a 10-foot barn, but rather in a 5-foot barn. So what the boy actually sees is the front edge of the ladder with him way out, 10 feet away from it. He sees the front edge of the ladder line up with the back edge of the barn. Then he sees the back edge of the ladder line up with the front edge of the barn. And his father stupidly closes the door. Meanwhile, he's done run through the back and left a Wile E. Coyote type hole in the back wall. And he's a little, dumbfounded because he just ran through a wall at 86.6% of the speed of light. So he's kind of in pain, right? And he's like, man, I didn't think that through. And the father's just sitting over here laughing because here's what happened in the father's frame. In the father's frame, the boy did in fact take off running, and therefore the ladder and the boy actually shrunk. So the boy still stayed, 6'3" tall, but his width shrunk this way. And in fact, the barn stayed the full 10 feet long. And the ladder did actually, in fact, easily fit inside. Because the father did just as the boy said, which was when the boy got right here, the back edge of the ladder was in perfectly line with the front edge of the barn, and the front edge of the ladder was perfectly in line with the back edge of the barn, and the father closed the door. So this is the father's frame. And this is the boy's frame.
So, Professor.
Yes.
I'm a little lost since I tuned in late because I had like a math test / midterm.
Yeah, no problem.
And it ran over. Yeah, and I'm just like mainly confused about I understand how this is like a paradox.
Mm-hmm.
But does that mean technically the ladder is 10 foot and the barn is 10 foot? Or is the actual length different?
The error is in the wording. There is no quote unquote actual length versus not actual length. Okay. When the ladder is not moving with respect to you, it's 20 foot long. When it's moving with respect to you, it shrinks.
So it's just a matter of perspective?
Sort of. And I'd say it's a matter of the reference frame you're saying, but yeah, that's in some sense perspective. So what's happened here is it seems two paradoxical outcomes, right? Either the ladder fit or the ladder did not fit. Well, the problem is there's a definition of what fitting is, and that definition hinges on something that we have to give away when we introduce special relativity. So we can no longer have a sense of universal synchronicity, right? The ladder fitting in the barn meant that at the instant the front edge of the ladder was lined up with the back edge of the barn, the back edge of the ladder was lined up with the front edge of the barn all at the same time. So in this frame, that was a synchronous event, and the father knew it, but was just, playing along. So in that reference frame, which the ladder was moving at 86.6% of the speed of light, it actually did fit. Now, in the reference frame of the person carrying the ladder didn't shrink at all. It stayed a full 20 feet long, but these events were actually not synchronous. So what he first saw was his front edge of his ladder lining up with the back edge of the barn. And then he saw his body running through the barn and then running through the back of the barn. And then a few instances later, he had the back edge of the ladder lined up with the front edge of the barn. And his father sort of in his frame stupidly closed the door like he'd done something. So you cannot say at the end of the day definitively the ladder fit or did not fit because of the definition of synchronicity, and synchronicity is a relative thing. So that's the importance of these two paradoxes, is you getting a deeper understanding of relativity and seeing one of the other things that we actually lost, which was synchronicity. We already lost the idea that lengths are not absolute, and we'd already lost the idea that time was not absolute. Now we've figured out that a difference in time being 0 is not absolute, because in this case, the difference in time was 0 from the front and the back lining up. To this time, that delta t, that change in time, was very much not 0. So that's what these two paradoxes are there to teach you. Plus, it also brings into account, the fact of length contraction. So you see another example of that. It definitely changes time a little bit, because if the difference in time is 0 here, then the difference in time is not 0. That means your times are inherently different, which we already saw with time dilation, but this is even slightly different from that. So any questions on that one?
So the father views it as like one frame, while the boy sees it as kind of multiple since he's running through it. And
yeah, the boy has his own frame since he's moving at 0.8 moving at a set speed. He can pretty much claim that one frame. And in that one frame, yeah, he saw multiple events occur. He saw the front edge lining up with the back. He saw himself running through the barn, and then he saw the back edge lining up with the front, and then his father closing it. But those things were a string of events with a finite amount of time between each of them.
Okay.
Okay.
That makes a little more sense.
Yeah, it's not, it's weird. It's in some sense is way easier to understand than quantum mechanics, but in another sense, it's still very hard to understand.
Yeah, it's still tough to like wrap my head around like paradoxes and like the conceptual stuff we go through.
Yeah, exactly. There's actually another one, and it's the spinning ring paradox, but I don't usually cover that in class, but you can check it out if you want. Basically, the scenario is if you take a merry-go-round that's spinning, a spinning merry-go-round, obviously the outer edge of the merry-go-round has a velocity v, right? Well, that circumference of the merry-go-round is a direction parallel to the motion. So you'd expect the actual circumference to shrink by Lorentz contraction because it's going at some velocity greater than 0. But we know the circumference is given by 2 pi times the radius. Well, the radius of the merry-go-round is perpendicular to the velocity, so that shouldn't change at all. So how the heck does the circumference change? And that seems to be a paradox, that the circumference only depends on 2 pi r, and r is perpendicular to the velocity, so r can't change, hence circumference shouldn't change. Yet we know for a fact Lorentz contraction is going to happen. Well, it turns out in order to do that, you've got to consider a series of reference frames with constant velocity at each instant in time, and you end up getting a whole different geometry on it. It's really cool. It's a geometry where, when you're a kid, you sort of think if you cover up your eyes, since you can't see your mom or dad, they can't see you, right? That's some stupid thing that kids do. Well, we know as we grow up that if we're in a position where we can see someone, if that person is mindful enough and has good enough vision, they can see us. There's no ifs, ands, or buts about it. There's no way you can hide from a person. Now, you might be smart enough to put a little mirror in the way, and then that person would have to look exactly in that little small mirror, but they still, in principle, if they hit that small mirror, they could see you. Well, on the geometry of this spinning disk, it turns out that light doesn't have that reciprocity. So just because you can see me doesn't mean I can see you. Triangles, in fact, are shaped like this instead of an actual triangle, rectangle.
So they're like curved lines instead of like straight lines.
Yeah.
Okay, is that because of the way the light bends?
It's actually, in some sense, it's the way space is starting to bend, really, because the geometry, the equivalent to a straight line is called a geodesic, which is a line of least time, and a line of least time turns out to be a curved line. So it's kind of weird, but anyways, y'all can look that up if you want to. Just look for spinning disk paradox. And I only saw it written up in one book and explained, but oddly enough, Ehrenfest, who was a good friend of Einstein's, he was the one that saw that. Ehrenfest is a really sad situation. He had a special needs son and ended up taking his son's life and his own life early on because it just got too hard for him. His wife had left him. It was just him. He was a brilliant man, and he ended up taking his kid's life and his own life just because he didn't want to live without his kid at the same time his kid was being treated horribly. So terrible scenario, but awesome physicist. All right, any questions about any of that stuff except for the death? I don't want to talk about any more about death. I had enough of that.
Well, I mean, aside from the fact that, you know, the amount of energy released from the sun hitting that barn door would be tremendous. But I believe at that point he would stop being biology and start being physics. But so right. What exactly is the point of discussing this? Is this just to understand that your answer will depend on the frame of reference that the question cites?
That, and also seeing what things are changed by relativity, because we had time dilation, so we knew time intervals varied, but we didn't necessarily know that a time interval equal to 0 could vary, right? Because if you look at the time dilation equation, you've got something times delta t 0. No matter what, if delta t 0, the other one's going to be 0. Or if delta t is 0, then delta t has to be 0. No ifs, ands, or buts about it. But time dilation can't show you that. So this is a whole different paradigm. This is something, a bigger discovery, where even delta t equals 0 is variable. So it allows us to start into the next part, which is the Lorentz transformations, which is really the way you convert your coordinates from one reference frame to another. Okay, so let me recap what we've written so far. Maybe this will help better understand it. The twin paradox was, of course, just understanding how you could test one person's claim versus another. If you can do some test to prove them wrong, then that person's claim is not valid. And that's what happened with my brother claiming that he was the younger one now. So what we've learned so far was that the time observed by someone on the bank next to a train or a moving car or a moving train car or whatever, that time delta t is equal to gamma times delta t 0, the time measured by someone in the car or on the train or whatever. We've also learned that the time someone measures, or excuse me, the length someone measures as a spacecraft is flying by them is equal to the length that the people on the spacecraft say the spacecraft has divided by gamma. So that's length contraction. This is time dilation. And now we found that simultaneity is relative. So that's some of the conclusions we've been able to make just from these little bits of pictures that we're using and stuff like that. So if you think about Galilean relativity, you might say, for instance, let's imagine a coordinate system. Now this is going to be a kind of weird one, say.
Wait, Professor, before you continue, I have a quick question. Where do you get the gamma from for those equations?
The gamma is defined to be 1 over the square root of 1 minus v over c squared, which is also 1 over the square root of 1 minus beta squared.
Okay, and then where would beta come from?
The beta is v over c, your velocity divided by the speed of light.
Okay, so velocity over speed of light, and then 1 minus that over 1 or under 1.
Right.
And that's how you get your gamma.
Yeah.
Okay.
Okay. So let's take a reference frame. Let's take this one right here that we are attached to, meaning we're sitting still, not moving. And let's take another reference frame, x prime, y prime. I'm taking some pains to make sure x, y, and z are all parallel, and also that at t equals 0, the origins coincide. Okay, that's important. You have to have this for these results that I'm going to give you. So at t equals 0, the origins have to be in the same place, and the positive x-axis has to agree with the positive y direction. In other words, they have to be parallel. Similarly, the positive y direction has to be parallel to the positive y prime direction. Okay. So what you might say is this thing is moving with a velocity v. So that's the difference in the reference frame. So what this person calls x prime, which is this quantity right here, okay, this frame is going to call x equal to x prime plus vt. Does that make sense? And of course, they're both going to agree. They're going to say x equals x prime plus vt. They're going to say y equals y prime, z equals z prime, and t equals t prime. And that's exactly what Galilean relativity teaches us. Well, it turns out when you actually work this out from a relativistic standpoint, and you can do this if you really like algebra, just try to make the distance light travel be the same in both coordinate systems. You know, there's a x minus x1, y minus y1, z minus z1, and t minus t1. And then there's the same thing for the prime coordinates, and you set them equal to each other, and then you try setting like y, z both equal to 0, and then lo and behold, you'll get another equivalent form of this. But in this case, the actual equations become x is equal to, I'm going to leave a little space here and you'll see y, is equal to x prime plus vt. That part looks pretty normal, right? That's just the normal x prime plus vt. Well, the difference is now in the Lorentz transformation, you have to put that gamma factor in there again. Remember, I told you how important the gamma factor was? This is why you just see it over and over and over again. But we still have y equals y prime. We still have z equals z prime. And here's the weird part. We're going to get t is not equal to t prime. In fact, it's equal to gamma. And not only that, times gamma, but also plus vx over c squared. Okay, this is Lorentz transformation. And all you have to do if you want to switch it to solve for x prime, y prime, z prime, and t prime is just put a negative in there. Replace the v with negative v, and you'll get the exact right answer. So it'll be x prime equals gamma x minus vt, x prime equals, y prime equals y, z prime equals z, t prime equals gamma t minus vx prime over c squared. Actually, that x prime is going to become x then. So that's the Lorentz transformations. And believe it or not, this is how you make these two coordinates systems match. All they had to do, of course, was have the origins at the same place at t equals 0, and that the x-axis had to be parallel to the x prime axis, the y prime axis had to be parallel to the y-axis, and the z prime axis had to be parallel to the z prime axis, and the motion is only along the x direction. Now, we've worked out in god-awful detail, for those of us that actually study relativity or had really tough professors in modern physics and stuff like that, we've actually worked out the coordinate changes even when the x, y, and z axes were not parallel. They still started with the origins equal to 0, at least in the one that I did. So there is actually further equations you can use, but this is just when they're going in one particular x direction. Okay. So that actually is what you need to solve some of the problems you'll see in your homework. You just got to pay close attention, because like one problem in your homework, I know for a fact, they give you like t, but they give you like x prime. And actually, this is supposed to be a t prime over here too. I forgot that. Sorry about that. Notice on the right side, it's always either x, y, z, and t, or x prime, y prime, z prime, t prime. The other side always has only the other things. That's what will keep you straight, because this is not really hard to memorize. So that's our Lorentz contractions, or Lorentz transformations. Now I'm going to show you something else, and we can actually derive all this stuff this way. Or you can actually, for instance, derive time dilation. You can derive length contraction from those things. I recommend you give that a try. Your book does it. But what I want to show you is what the addition of velocities is. And we did this back in like chapter 2 or 3. I gave you what the relativistic addition of velocity formula is. But we had before that the velocity of A as seen by C is equal to the velocity of A as seen by something plus the velocity of something as seen by C, meaning the outer subscripts have to match. And then the inner subscripts have to match each other. So I could put, for instance, B and B, and I'd get a correct equation. That was Galilean relativity. I then told you, in actuality, as long as you keep them, in this case, as long as you keep them along the same axis like those two reference frames were, then velocity of A as seen by C is velocity of A as seen by B plus velocity of B as seen by C. But there's a correction to it for relativity, and that's VAB VBC over C squared plus 1 in the bottom. Okay, so that's the addition of velocities formula. Okay, and remember it has the rule that Vij is equal to negative Vji. Excuse me, I. Vj. It's really terrible. I'm reaching so far from my seat, I'm writing really badly. Vji. So when you reverse the subscripts, you have to multiply it by a negative to keep it equal. So there's another formula you can use. I've shown you some examples. You can look back in, like I said, chapter 2, where I did one of those. We can even do things like, one spacecraft is flying towards another spacecraft. Both are going at like 80% the speed of light, and one fires a photon torpedo, weird stuff like that. So let me give you one example, and I'll call it a day after this. What we have left after this is introducing relativistic momentum, which I can tell you P is going to be gamma mv instead of just mv like we knew. And we're going to introduce, so you can start using these equations automatically, by the way. So we're going to introduce the summation of forces is equal to, again, dp dt, but this is the P now. Okay, so that's the actual P you have to use with Newton's second law. From that, you can also get that E equals mc squared. And that's true for all energy. For instance, if you do that, Joseph Priestley, I think he was one who did that experiment, where he weighed some wood and then he put the wood in a closed container and burn it, and then collected all the ash and debris and all that stuff, and he measured the total mass, and it added up to be exactly the same as the mass before he burned it. If you actually do that experiment with enough decimal places, you'll find that the mass of the ash and everything is slightly less than the mass of the log, and the amount it's less will be actually equal to change in mass equals the energy created by the fire divided by c squared. So this equals mc squared is true everywhere. If you took all the exhaust from your car and compared that mass to the mass of your gas tank before you ran it, the mass of the gas in your tank before you ran it, you would see that mass difference would be different by how much energy was created divided by c squared. And then if we have that, we have kinetic energy is equal to gamma minus 1 times mc squared, no longer 1/2 mv squared. So those are where we're going. You can start using those equations immediately, but what I wanted to show you is one example here. So let's imagine a spacecraft traveling at 3/4 c towards another spacecraft. Let's call this A, let's call this B, and another spacecraft traveling at 7/8 c. Then the velocity of B as seen by A is equal to, and this is relative to Earth, so I'll put an E on it. The velocity of B relative to Earth plus the velocity of the Earth relative to A divided by 1 plus VBE, VAE, or EA, excuse me, over C squared. Well, what you got to realize is we're going to choose one way as positive, so I'm going to choose the right as positive. So the velocity of B as seen by the Earth is actually negative 7/8 C, plus the velocity of the Earth as seen by A. Remember, the velocity of Earth as seen by A is equal to the negative of the velocity of A as seen by Earth. So I have to now make a negative out of that. So I'm going to say minus or plus negative 3/4 C. And then this will be divided by 1 plus 7/8 C negative times negative 3/4 C over C squared. You can see the C squareds cancel out. This is the same thing as 6/8. So 6/8 plus 7/8 should be what, 13/8? So that'd be 13/8 the speed of light negative. That's what Galilean relativity would give us, would be 13/8, right? But it's corrected by this factor down here, which is plus 1 plus a product of negatives is positive. So it's going to be 1 plus, I'm going to take 7 times 3, that's 21. And I'm going to take 8 times 4, that's 12. So this will be 12 12s plus 21 12.
That's 32, sir.
Oh, thank you. Oh, I multiply, I added, so thank you. Yeah, 8 times 4 is not 12, oddly enough, it's 32. And this will be 32 over 32. So 32 plus 21 would be 53. So it'd be 53 30 seconds under 13/8 C, which I can take and make it 13/8 times 32 over 53. Obviously, this is 4 times 8, and this is 8 times 1. So that 8 is going to cancel out with that 8. And 13 and 53 are both odd, or excuse me, are both prime. So we shouldn't be able to make any cancellations there. So 4 times 13 would be 52. So negative 52 53rds C. So it did get a lot closer to the speed of light, but it's still not going to exceed the speed of light. You can now add to it, for instance, a photon torpedo, which relative to A would be fired at a speed C. And you'll find that this approaches this one. In other words, you do the velocity of the photon relative to B, and you'll see it still turns out to be C. So our time's up. You guys are free to go. But that's some more problems that we've now solved, and hopefully it'll help you. Anybody have any other questions?
Are you going to be making the test available today?
Yes. Thanks for reminding me, though. Let me write that down before I forget.
Will there also be a practice test for chapter 9 and 10?
Yeah. Oh, if I haven't set that up yet, then yeah, I will put the practice test up today, and the test will not be due until till Wednesday, because I always give you at least a week.
Yeah, let me quickly check and see if you have it up.
I might not, and like I said, I guarantee you guys I want to give you a whole week. Okay, I'll put that up first, and then I'll probably wait until Friday and put the test up then.
So do you have any like student hours? Because I
do them as needed. So if y'all need any, you can stay after class.
I would email you?
Yeah, or
Can
you
I
can
email you
email
and
to
set
set
up
up a
one?
Zoom meeting, or you can stay after lab or come early to lab. Yeah, any of those are cool. You might want to text me though when you want something urgent like that, because I'm supposed to get back to you within a day, but sometimes I completely miss emails.
Yeah.
So feel free to text me. That's why I gave y'all my phone number.
Okay. And just during the weekdays is the times?
No, I can do weekends too.
Oh, wow.
I'm always checking my phone. Yeah.
Okay. And today's lab will be like lab 9.
Yes, if I remember correctly, we're doing projectile motion.
Okay, thank you.
No problem. Anybody else have any questions? Brandon, Brian, Gavin?
Oh yeah, you You said so. You mentioned something concerning lab. Like we're still having lab today and everything.
Yes, yes. I told my students that one of my students said I accidentally set the lab for being due tomorrow at like 8:30 or something. That's probably an error, but I'm sticking to it since I did that because a lot of people.
Oh, you mean last week's lab?
Yeah, last week's lab. Yeah.
Okay.
Yeah, so that's when that one's going to be due.
Okay.
Okay.
All right. Thank you.
No problem. Jacob, Joshua, Matthew, Randall, Richard, Ronnie, Johnny, Ricky, or Mike, Vincent. Hey, Matthew, how do you actually pronounce your first name? Just out of curiosity, if your speaker works. Is it Matvey? Matvia? I don't know. He might not be there. All right, guys. Well, y'all have a good one. I was just wanting to be a little bit more educated on other languages. So neither here nor there how he pronounces it, but he was kind enough to let me pronounce it, Matthew. Y'all have a good day. And if you have lab today, I'll see you at 1. If you don't, I will see you Friday.